Exactly. Thank you for the kind introduction. Hello, everyone. I'm very glad to be here and thank organizers and all the participants of this outstanding workshop. And indeed, I'm going to tell you about topological states in confined ferroic nanostructures. And just I will start with the explanation why I say ferroic, because I will describe the textures, the order parameter textures, which appear in two different classes of materials, ferroelectrics and ferromagnets. Thanks to Lucas and his talk today, I don't need the introduction to ferromagnets, but I will remind you briefly what ferroelectrics are and how they are similar and different to ferromagnets, and which textures, not spin textures, but really similar textures can be observed in those materials. And I will show you possible two-dimensional and also three-dimensional structures arising in ferroics. What actually are the ferroic materials? So all the materials which have this word with part ferro in their name have this name because they show similar behavior to ferromagnets. So with the undergoing phase transition below a critical temperature and having a vector order parameter to describe the properties in continuum theory, you can do similar thing to describe ferroelectrics with polarization, ferroelastics with deformation vector, and also there can be antiferromagnets, antiferroelectrics with their own vector parameters, and multiferroic combining several kinds of order parameter ferroic ordering. And what's important that you have this phase transition to ferroic phase and the vector field which describes the material in ferroic phase. But in my talk, I will actually stay with more studied and experimentally accessible ferromagnets and ferroelectrics. However, the consideration which I will talk about are pretty general, so they can be applied to any material which has this vector field ordering. So a brief reminder what actually is a ferroelectric. So a ferroelectric material is a polar dielectric which has spontaneous polarization as order parameter which can be switched between different states, two or more, with application of electric field. So this switching behavior is pretty similar. It's pretty similar to what one observes in ferromagnets, showing the hysteresis loop. And like textbook example of a ferroelectric is a perovskite oxide, which, due to central atom shift, can possess the spontaneous polarization. Basic properties of ferroelectrics are shown in this slide. So they have high permittivity, which is ability to polarize and undergo various structural transitions with temperature or pressure, for example. And a peculiar feature is a strong electroelastic coupling, which results in various electromechanical effects. When coming to the nanoscale, it is important to know that ferroelectrics are also somehow different from magnetic materials. So first of all, polarization can acquire any amplitude. So we know that in many magnetic materials, spins cannot vanish to compensate the structural interactions, but polarization can actually vary in space and also vanish. So there can be points in the nanoparticle in the material where polarization is equal to 0. I will repeat that the polarization is strongly coupled to elasticity, to the mechanical degrees of freedom, which is a rare situation for ferromagnets. So usually the magnetic restriction is in ferromagnets is low and neglected. It's different for antiferromagnets, but well, for ferroelectrics, strain is one of the important tuning parameters, so this large coupling. and large coupling with electrostatics. So the dipole-dipole interactions in ferroelectrics are crucial. So we already know that in ferromagnets, dipole-dipole interactions also lead to important results. They are difficult to handle, to calculate analytically, to model. In ferroelectrics, it's pretty much the same. And it is important that divergence of polarization, abrupt change in polarization at the nanoscale, creates charges which produce large energy. So if you take a ferroelectric slab, like nanofilm of ferroelectric, uniformly polarized in perpendicular direction, it will appear at the surface of the slab will appear depolarization charges. So the whole system serves as a capacitor and creates electric field, depolarization field, which is directed oppositely to the polarization and actually was thought for a long time to destroy ferroelectric order. So for many years, it was believed that, that ferroelectricity cannot exist at nanoscale at all due to this effect. But actually, this was predicted theoretically like 20 years ago that will happen quite a similar thing to magnetic situation, that at nanoscale the configuration of interactions will favor the creation of striped domains. So the sample won't stay uniformly polarized, but will acquire non-uniform structure in which the polarization field will be a surface effect. So due to alternating charges on the surface, the polarization field is localized at the surface of the film, and so with additional cost of creation domain walls, it will result in a stable configuration. So at the nanoscale, ferroelectric texture exists, and it can be non-uniform and similar to magnetic domain structure, for example. And due to this property of avoiding polarization charges, many different non-uniform textures may appear depending on the configuration of the system. In nanofilms, nanoparticles, nanodots, there can be different geometries where, in order to avoid this abrupt polarization change at the surface, system creates fancy non-uniform structures. Mathematically, this requirement of having zero charges can be written as zero divergence of the order parameter field. So those structures, ferroelectric structures, were observed actually experimentally in recent years. So I guess first to observe was this vortex-anti-vortex structure in superlattices, and recently also these skyrmion lattices in polar skyrmion bubbles in similar superlattices were observed experimentally. And in last 10 years, there was a variety of structure simulated, predicted, and experimentally measured, including different types of domains, vortices, arrays of vortices or merons or skyrmions, and also in 3D geometry, like nanoparticle, there was shown that this non-trivial noted soliton called Hopfion may also exist as a ground state. So how to describe a ferroelectric? The theory is like a continuum theory which we use for any ferroic material with its peculiarities. So we have this phenomenological Ginzburg-Landau energy, which is the expansion of the free energy in series over polarization components, and gradient or exchange energy, electrostatic energy or dipole-dipole, and elastic energy that we also have to take into account. Note that compared to magnetics, there is no antisymmetric exchange, so nothing like DMI, for which would be added to for magnetic materials. And since the amplitude of the order parameter, since polarization is not constant, we have to keep all the terms and not just leave the anisotropy terms as for ferromagnets mostly. Also, if there is an external field, it also added to the model. With using this functional, we started our first system, which is a skyrmion bubble in a nanodot. So the nanodot made of lead titanite was modeled as deposit on the substrate, and a gate created an electric field in this system. And it was shown that there can appear 4 different skyrmion types in this nanodot, which are described by just left-right hands and up-down polarization in the center. And it is possible to switch between all these states with electric field. So in comparison to the magnetic skyrmions, these structures are interesting because they all have the same energy and no chirality is energetically favorable. So the chiral structure appear not because of the intrinsic Dolachinsky-Marie interaction or other antisymmetric exchange, but because of the confinement. So this is a particle, this is not an infinite system, so it has surface, and electrostatics, which wants to avoid the creation of depolarization charges. So we solve the equation of relaxation with finite element modeling. We call it phase field modeling approach, similar to micromagnetic simulations. And we obtain...
What is gamma?
Gamma is damping, so just a parameter of relaxation for modeling is just, since this is not a dynamical problem, so it's just static relaxation, it's not important for our modeling somehow. So if we want to model dynamic properties, so we have to think about the like typical time of relaxation of this system. But here it's just to get the system evolve into stable state. We show this switching process in the skyrmion. So here you see the particle coming to 1. So this is a video going through all the switching states when we apply electric field and then go back and forth like in opposite directions, so we apply field in opposite directions. And we see indeed that with the application of electric field, we can destroy a skyrmion and create a skyrmion bubble. So let's say bubble because no intrinsic interaction. And create a skyrmionic bubble with the opposite chirality. So at the moment the blue, the main wall for this skyrmion appears. So this is these skyrmions are block types because Néel skyrmions are not favored for the same reason that for the electrostatic interactions and the necessity to avoid the depolarization charges. Interestingly, in materials with the pronounced magnetostatic interaction, which are rare guests in magnetic papers, because usually you want to have your model solved, you want to have a thin film to not take into account magnetostatics, and actually a material which itself has low magnetostatic interaction. But sometimes you are unfortunate, and experimentalists at our institute just created this multi-layer structure, which is 6 layers, 8 nanometers each. So 50 nanometers is like much more than you can afford to neglect magnetostatics. And they observed, with 2 techniques, they observed the skyrmion bubbles of Néel type in this structure. So we were trying to figure out what stabilizes those bubbles in their structure. And so I found out theory of skyrmions stabilized by magnetostatics in films of arbitrary thickness. In this paper, they give reasonable expressions, reasonable approximations for all the energy terms, and actually show that magnetostatics can stabilize a skyrmion bubble even if DMI is absent in the material. So just because they exist magnetostatic interaction. So we managed to apply this theory for the material which was measured here experimentally. And so we found out the following. So this energy can be split into two contributions, so-called domain wall energy, for terms which are linear, which increase linearly with the increase of skyrmion radius, and the contribution of bulk energy, which is magnetostatic contribution and external magnetic field. And it was shown that actually for this system, the bubbles that they observe are of hybrid magnetostatic and DMI nature. So we managed to estimate the DMI for this system that they created, but we showed that the DMI itself, which is like this domain wall energy, does not have a minimum, so it does not stabilize any skyrmions. However, if there would be no DMI, the bubbles would be of much larger radius, and they would be of block type. So taking into account both of these contributions confirms that for these materials, they exist skyrmions of radius of about 80 nanometers, which have an AL profile thanks to the DMI interaction, which is also present in this material. So these dipole-dipole interaction, magnetostatics in this case, can also lead to stabilization of skyrmionic bubbles in magnetic materials. Now I proceed to the 3D case and explain which structures appear in nanoparticles, 3D nanoparticles. Here I start with some mathematics. There exists Arnold's theorem of hydrodynamics. So yesterday, I guess, hydrodynamics was advertised for another fields of condensed, for another fields of physics. Let's make it general. So in ferroics, hydrodynamics can be useful as well. So in fact, this theorem claims that for a vector field which divergence is 0, the vector field lines, streamlines, can be organized in two ways. They either swirl around the cylindrical surfaces, which results in appearance of vortices or helices, or they swirl around nested tori. So each streamline lies on the surface of a torus. It was shown, proved, this theorem. And so, since we have the similar requirement for the polarization in ferroelectrics, we can use methods of hydrodynamics for these fields to describe our vector textures in ferroelectrics. So now it looks similar. So we just consider our textures, our vector fields as streamlines, linking somehow, filling up the space that they have due to the geometry and confinement of the material. And we adopt these hydrodynamical descriptions for our vector textures. So some hints what actually is used. So first, this is like a mapping of the coordinate space to the parameter space, magnetization or polarization. The example is usually shown for skyrmions when you map the hedgehog on a surface. So you can do that similarly for different types of topological excitation. So vortices is super easy. So also this hydrodynamical approach allows description in terms of streamlines. So if you can integrate streamlines instead of finding vector field in every point, you can also come to the notion of this topological chirality through linking number. So, and it can be calculated like for polarization vector field with this expression. And so for chiral structures like helices or hopfions, it can be shown that they can be of different chirality. And also for the field of zero divergence, it can be useful that you can apply the poloidal toroidal decomposition of your vector field. So separate the variables into a vortex part, which is usually easily solvable, and the the other part, it's called sometimes anapole in literature, so that the sum of these two vector fields will give you a Hopfion. And I start with the boring example of just briefly mention that first we tried to find textures in cylinders of PTO, and we see that polarization lead titanite, and we see that polarization arranges in some type of vortices. So depending on the geometry for low cylinders, the vortex is in plane, like what we usually call vortex. For larger cylinders, the vortex core turns perpendicularly, so we have like two domain walls and like a domain wall and two domains closing the structure, but somehow it can be also seen as a vortex. So it's still a vortex, nothing else. And we tried different geometries. So these two types of vortices, I'll probably skip it. And so for intermediate geometry, we found some more fancy state, which you see here. So in which the core of the structure looks like this, but it's still a vortex. It's just a vortex with a deformed core. So it just, the surface of the core changes along the cylinder axis, but it's still a vortex. So we found lots of vortices. Everything in this cylinder was a vortex, no Hopfions.
How do you differentiate between vortex and different structures? Because here it looks like
it's actually topology. So if you take a streamline of this structure, you see that each streamline does not link with any streamline. So this is like deformed cylinders. So the surfaces which this vector field turns around are just super deformed, like cylinders in their general meaning. So there is no linking. And there was similar experiments of O'Donnelly with magnets when they just found interesting structures, magnetostatics, stabilized interesting structures in a bulk magnet, and then they calculated the linking number, and unfortunately it was just rings, so no Hopfions. It still looks fine, but everyone is looking for Hopfions, and just not yet. Well, I am saying not yet, but these are two papers on magnetic Hopfions. One is theoretical. There are more papers, but these are probably the most known. So this is a theoretical paper by Rybakov, in which they stabilize the magnetic Hopfions by additional exchange interactions, not magnetostatics, but they offer another method of Hopfion stabilization, and it seems to be working, but it's, I don't know if those materials are found yet with having this really special type of exchange interactions. And there is one experiment in which they actually obtained a toroidal structure, Hopfion-like structure, but to obtain this structure, they had to create this material really, okay, it doesn't work. So really anisotropic, no it does. So the anisotropy and DMI of this structure changes along the axis of the material. So in fact, they fabricated material in such a way so that each next layer will turn the magnetization a bit, and that's how they obtained a Hopfion. So it's great that someone could see a Hopfion, but somehow it's not the same that spontaneously like creating this state of a vector field. So in ferroelectrics, Hopfions were obtained numerically, so using the same phase field approach. We showed that okay. So we showed that the Hopfion is formed in spherical nanoparticle in the following way. So if you take the uniformly polarized material and take like a spherical nanoparticle of it, it immediately, or just if you maybe go from paraelectric state, you lower the temperature, and the first state which occurs is a vortex state. So it's usually the state with lowest energy, and it immediately occurs. However, if you go far from the phase transition to room temperatures, the system tries to reorganize in a way so that the polarization is more or less, the amplitude of polarization is more or less homogeneous inside a structure to avoid this extra exchange energy inside. And is in this, in figure C, you see the lines, the vector lines escaping in third direction and creating this helix, and then vector field lines do a turn and just go down, and the Hopfion appears. So it was, yeah, and the spherical particle is looked like that. Exactly as the Arnold's theorem predicted, we have the system separated into several parts where it can Hopfions or vortices exist. If you make your system larger, you may have probably more like fractions over different textures, but for a nanoparticle small enough, there is a single Hopfion existing inside. So this I explained already. And what was also done, so it was similarly to Skyrmion's for two-dimensional case, it was shown that the chirality of Hopfion can be switched by the application of external electric field, and in fact Hopfion exists even when the electric field is off, but you can just destroy it by application of electric field, and then by applying field in the opposite direction to create the Hopfion of the opposite chirality. So it's super slow. Just you'll see the other torus. So you see that with the application of electric field, first the internal like torus appears, and then the vector field continues organizing, and so this is like the stabilized Hopfion. So now it gets destroyed, and then will appear with the opposite chirality. This is basically the end of my talk. What I tried to, which ideas I tried to highlight, that non-uniform textures of other parameters similar to those observed in ferromagnets can also exist in other type of ferroic materials like ferroelectrics. They have lots of common. They have their like peculiar features which help to describe them. And some of methods which we use to describe the ferroelectric textures, like topological approach, electrostatics methods, can be also adopted to describe magnetic materials with similar topology. And that like interesting approach to describe these textures is these hydrodynamical descriptions, which allows to see everything like a combination of vortex states and Hopfion states. So I want to thank all the people who worked with me on different parts of this research, and thank you for your attention.